Hello guys. Today we are going to discuss about mobility effects. So if you have seen my previous video, we discussed about transport phenomena, carrier transport phenomena in semiconductor devices. There we said the electrons in the conduction band, and in the valence band, holes in the valence band. Okay, actually are responsible for the process of conduction. Okay, or we discussed what is drift, carrier drift, and what is drift current density, and we derived expression that the total drift current is given by E times mu n times n plus mu p times p multiplied with E. Here we said this is the drift current density, this is the electronic charge, mu n is the mobility of the electron in the conduction band, n is the concentration of electron, mu p is the mobility of holes in the the valence band, p is the concentration of holes, E is the applied electric field. So this is what we said. Now we need to see how this mobility will be affected. Okay, in a normal semiconductor, if you will consider at room temperature. Okay, so how this mobility, this mu n, mobility of electrons or mobility of holes, will be affected, because if this mu n and mu p will be affected, then definitely your current density will also be affected. So we need to understand how this mobility will be affected. So today we are going to discuss that, the mobility effects. Okay, so if I'll write the equation of motion of a positively charged particle in the presence of electric field, what we will write. So the same thing I'm going to discuss what we have already written in the previous video. So if I'll write F is equal to ma, Newtonian mechanics, and that can be written as F is equal to your electronic charge multiplied with the applied electric field. So we can equate these two. So here this is your electronic charge, positive charge, and the applied electric field. But if you are writing it for a positively charged hole in the valence band, we know that the mass of the hole or mass of the electron, okay, that mass of the positive charged hole or mass of the electron will be different in the conduction band and valence band of a semiconductor. So if you have seen my video, in one of the videos we have discussed what is effective mass of the electron, if what is effective mass of electron and what is effective mass of hole. So this is the mass of electron in the conduction band, mass of the hole in the valence band, which we call effective mass of the electron or effective mass of the hole. So the same thing, if I'll write for positively charged hole, we can rewrite it simply mp star, where mp star is the effective mass of the hole in the valence band multiplied with the acceleration is equal to ee, right? So now this acceleration is the rate of change of velocity, so that is nothing but the drift velocity, as we have already discussed. So I can write this as mp star, effective mass of the hole, and let us write this is the rate of change of the drift velocity, dvd. For drift velocity I'm writing, and dt. Okay, where this vd we wrote for drift velocity. Okay, this is for drift velocity we are writing, right? So this, okay, can be written as e times e. Okay, this we can write. Now if we'll from here, if we'll just rewrite it again. So if I'll write d vd, the variation of the drift velocity can be written as e, okay, divided by this mp star here. This mp star will be divided here, so you got mp star over here, and then dt. Okay, so what we got is this. Okay, so we got this dvd is equal to this, right? So now further we can just considering this electric field, and the effective mass of the hole in the valence band to be constant, and we can integrate both the sides, so that we can rewrite it as what, vd, integrating both the sides, and considering the electronic charge is constant, you consider electric field to be constant, and this mp star to be the constant, so we can take it out. Then you got this. So vd, the drift velocity, Now we wrote in terms of, you can see the time factor over here, electric field, effective mass of the hole. Okay, so now what we can do is, in this expression which we wrote as vd is equal to E times E divided by MP star. Okay, and this is your T. Now this is what we got simply, the Newtonian mechanics. MP star is equal to E by small e and capital E. Okay, and from that we got this. Fine. Now what we will use is, okay, suppose the mean time between collisions. So we said the holes are actually moving in the valence band, right? So and we said for the conduction to happen, maybe the movement due to the movement of the hole or due to the movement of the electron, there must be electronic states available in the valence band and the conduction band. Then only the motion will happen. Now, when the motion is happening, the holes are moving in the valence band or the electrons are moving in the conduction band, what will happen? We said they will be like, interacting with other, like, electrons or holes. So this way, so if you will consider any kind of collisions, right? So if you will consider the mean time between collision, okay, mean time between the collision of these holes while moving in the valence band, okay, let us consider that to be some tau and cp I'm writing. So tau for time I'm writing, c for collision, and p for the holes. Okay, this way I just wrote on a notation, it's nothing great. So tau is for time I'm writing because it gives you the relaxation time, is the time between the two successive collisions. Okay, so time between collisions, that's why I wrote tau, c for collision, and p for hole. So let us use this notation to, you know give you the time, the relaxation time, or okay, or you said the mean time between collisions for an hole. Okay, for a hole, sorry. Okay, so you can write this way. Now if you will replace this t, if you will replace this t with this tau cp, okay, okay, then what we can write, this vd, the drift velocity which we wrote earlier. Okay, now this drift velocity we can write it to be what, vd, that is the drift velocity, or you can say the peak drift velocity, or the peak velocity, or the maximum velocity. So suppose this, okay, what I will write, that's the maximum velocity which we can write e times, okay, so what we said, E times E, capital E, okay, that's the applied electric field, divided by MP star, which is our effective mass of the hole, okay, multiplied with what, tau Cp, tau Cp. So this gives you what, the peak velocity just before the collision, just before the collision, because tau Cp is the mean time between the collision. So if I will take T to be the maximum value, that is tau Cp, then my drift velocity value will also increase, and that's the maximum value just before the collision, just prior to the collision, right? So here, this way we can write. Now if you'll write what is my mobility, the maximum value of mobility, we can write, this is our v d, whatever peak maximum velocity we got, divided by divided by e, because we know that the drift velocity, we said, is directly proportional to your applied electric field, and the drift velocity is equal to mu e, and there only we define mu as what, the mobility, right, or the proportional factor, which is mobility, right? So we can divide this, then you can write it to be what, E times tau Cp. Okay, that's the mean time between collision for hole. Okay, divided by what? Divided by your MP star. So now you can see this mu p, the maximum value of mobility of hole, is a function of this tau Cp, that is the relaxation time or the mean time between collisions. Okay, and also the effective mass of the hole, effective mass of the hole. E is the electronic charge, which is constant charge of the hole. Okay, so these are the parameters we can write. The same way you can write for the electron. Okay, so similarly we can write it for electron. Suppose I will write for mu n, that is the maximum value of mobility of the electrons in the conduction band now. Okay, can be written as the magnitude E tau Cn. What is tau Cn? Tau Cn, we will say it is the mean time between collisions for the electron, right? So E tau Cn divided by what? The effective mass of the electron in the conduction band. Okay, so if E tau Cn divided by Mn star. So this is what we can write. Now finally what we got, the maximum value of mobility of the hole and the maximum value of mobility of the electron in the valence band for hole and in the conduction band for the electron can be written as by this tau Cp, which is the mean time between the collision, divided by effective mass of the whole. Okay, and similarly here E tau C n divided by M n star. So now you can see of major factor which is here, what you said is collision here, collision. Okay, collision between maybe the maybe between the lattice atoms, or maybe between electrons and electrons, holes and holes, whatever. Okay, so this collision, this time factor will decide actually how the mobility will be affected. And now this mobility, once you got the mobility, will decide what will be the drift current, for a certain value of applied electric field. In addition to this, what we got is we got two other parameters which we said, this MP star and this is Mn star here. Okay, so effective mass of the electron and holes, that will also effective mass of electrons and holes in the conduction band or the valence band respectively will also decide what will be the current density. Okay, so now after this we got, like, what is that collision process actually, okay, or the scattering mechanism that dominates in the semiconductor and which will affect the carrier mobility, this carrier mobility mu p and mu n. So what are those collision, okay, phenomena or mechanisms that actually dominate in, that happens in this semiconductor and dominates the whole process? So if you will consider that, then we can consider, we can write, actually there are two different types of collision mechanism actually we will see in a semiconductor. One we call as Phonon or lattice scattering, lattice scattering. Okay, and the other, the second one we call as ionized impurity scattering, ionized impurity scattering, ionized impurity scattering. Let us see what is this, phonon or lattice scattering or ionized impurity scattering in detail. Okay, so what do you mean by phonon or the lattice scattering? Okay, so let us do that. Phonon or lattice scattering, when we said, suppose lattice scattering, what do you mean by lattice scattering or phonon scattering also you can call it, lattice scattering or phonon scattering? If you'll consider the atoms in a semiconductor crystal, okay, so all these atoms will have a certain amount of thermal energy, okay, at any temperature above the absolute zero, that we know, because at absolute zero the molecular motion ceases. So we consider that there is no actually movement of the there is no thermal energy. Okay, but any temperature above this absolute zero, these atoms will have certain amount of thermal energy. Okay, so which will produce or which will cause the atoms to vibrate randomly, okay, about their lattice position. So what we said, in any atom, if you will consider, we said these, sorry, in any crystal you consider these are the lattice points. Okay, or this is the way actually the atoms are arranged. Okay, with a average separation, you said lattice constant or whatever. Okay, so this is known as the lattice constant. So anyways, so these atoms with respect to their lattice position here, okay, which is considered to be the equilibrium position, they randomly vibrate with about this particular position, okay, at any temperature greater than absolute zero. So any temperature absolute greater than absolute zero, these atoms actually they oscillate randomly. Okay, they oscillate randomly. Okay, with respect to their mean position or lattice position, we said. Fine. Okay, now a perfect when we, we have already discussed in one of the videos initially. Okay, in chronic penny model and all, so we said these lattice atoms actually they create a perfect periodic potential. So if you have done or you have not seen this way, you can see actually if these are the lattice positions of the atoms. Okay, they actually create a periodic potential, like periodic potential like this. periodic potential. Okay, this we the periodic potential. So that's the reason we used chronic penny model. Okay, to understand this periodic potential. So we said there is a periodic potential like this. Okay, exists. Okay, and the electrons or the holes, they move through this periodic potential. Okay, they move through this periodic potential. So now what I said, a perfect periodic potential in a particular solid or in a crystal allows the charge carriers, these electrons or holes, to move undisturbed. Okay, or without any scattering through the crystal, without any scattering through the crystal. But because of this, temperature, you said T is greater than 0 Kelvin, and these lattice atoms, they are oscillating randomly with respect to their mean position. Okay, now what these vibrations, thermal vibrations will cause, it will cause a disruption in the potential function that is defined over here. The potential function will now be disturbed. Okay, so which will result in an interaction between what, the charge carriers which are moving through this solid or through this crystal, right? So interaction between the electrons or holes and the vibrating atoms, lattice atoms, will occur, right? So this particular interaction, or we said the scattering, is known as lattice scattering or Phonon scattering. So what we said, simple, electrons or holes, they are moving through this, this crystal. Okay, while moving through this crystal, actually if the electrons are not randomly vibrating, then they create a periodic potential through which the electrons or the holes, okay, can easily move through, right? Okay, but because of this random vibration at certain temperature greater than 0 Kelvin, they will interact with these vibrating lattice atoms. Okay, and it will undergo like collision. Okay, this kind of collision, or this process of collision, is known as lattice scattering or Phonon scattering. We said Phonon scattering or lattice scattering. Okay, so now this lattice scattering, this process of lattice scattering is actually related to what? The thermal motion of the lattice atoms or the atoms. Okay, so the rate at which the scattering occurs. Okay, so what we said now, the rate at which, the rate at which the scattering occurs, the rate at which the scattering occurs, okay, is actually a function of temperature, as we said, because the temperature increases, then the random vibration will increase, and it will affect the mobility of the electrons or holes or the charge carriers through the crystal, right? So using scattering theory, which we have not we are not discussing here, we may discuss it in some other video. Scattering theory, using this scattering theory, it can be shown that the mu L, which is what, the mobility due to lattice scattering. Okay, so mobility due to lattice scattering is proportional to what? Temperature to the power minus 3 by 2. Okay, so this is what we said. Hence mobility will decrease, mobility will be affected, okay, as the temperature, as the temperature is increasing or decreasing, so mobility will be affected. For example, here the mobility will increase as the temperature will decrease. You can see the negative sign, T to the power minus 3 by 2, right? So the mobility due to lattice scattering will increase, okay, as the temperature will decrease. Temperature will decrease means what? The vibration, random vibration will decrease. So the the periodic potential of the lattice atom created will be less disrupted. So less disrupted means the charge carriers can move smoothly, right? So this is what we understand by lattice or Phonon scattering, and how the mobility will be affected by this. Now there is a graph actually, an experimental graph that can be taken into consideration. So if you will take temperature in degree Celsius here, and then the mobility of electrons, mobility, the unit is actually, we have already discussed in one of the videos, centimeter divided by volt second. So this is suppose here you are plotting it, and then you have mobility, like different values you can take, and for different doping profile, like different donor impurity concentration, the graph looks like little linear, and then like this. Okay, for different doping profiles, suppose you have some Nd is equal to Doping profile means the number of impurity you have added per centimeter cube, 10 to the power 17 atoms per centimeter cube, or 10 to the power 18 and 19, that we you just keep on adding. And I suppose here nd is equal to 10 to the power 18. So this is how the graph of mobility varies with temperature. Okay, so as the temperature increases, you can see there is a decrease in the mobility of the electrons in the conduction band. Okay, so this is how it looks like. Okay, then come to the other type of scattering. The second one we said, that is ionized impurity scattering. Ionized impurity scattering. What happens in this case? What happens in this ionized impurity scattering, and how the mobility will be affected because of this ionized impurities? Okay, so as the name suggests, okay, we know, and we have discussed in extrinsic semiconductor, just to increase the number of charge carriers, either electrons or the holes, we need to add impurity to it using the process named doping, right? Doping process, right? So now impurity atoms are added to the semiconductor to control its characteristics. Characteristics means concentration of electrons can be regulated, so that your current characteristics can also be altered or changed, right? So these impurities are ionized at room temperature. Already we have discussed in extrinsic semiconductor. So we said you have conduction band over here, you have the valence band over here. When you are adding pentavalent impurity to it, it will create a donor energy level over here, ED. These electrons, donor electrons, are loosely bound here in the donor energy level, and the order of the energy required is of 0.01 electron volt. We have already discussed what is ionization energy in some other video. You can refer to that. So at any small thermal agitation can actually make these electrons elevate to the conduction band from the donor energy level. So you got these electrons elevated, shifted to this conduction band, and here you got actually immobile positive ions now. So these electrons were gone, and here you got immobile positive ions. So immobile positive ions we got here. So no, this, sorry, negative electrons further. So we got here positive ions, immobile ions and fixed ions, we said. Similarly, if you are adding, like here we said donor impurity, you added nd. Similarly, acceptor impurity, if you add, then similarly what will happen? The negative ionized impurity will be developed in the semiconductor. So these impurities, okay, what they will do, there will be a Coulombic interaction between these impurities that we considered here, impurities here in the positive ion, and here you can see there is a Coulombic interaction between these positive and negative charges, right? So because of this Coulombic interaction, when these electrons will move in the conduction band, their motion will be affected because of this Coulombic interaction, okay, which exists between the electrons or holes in case of acceptor impurities and the ionized impurities. Okay, the same thing can be done for actually the holes. So you have the EV here and EC here. Your acceptor state will be somewhere here close to this, and the similarly what will happen here, we said acceptor state, so electrons will be elevated to this, right, these acceptor states. Okay, so what we got here, you got holes over here, these are the holes you got. Okay, and here you got this negative impurity, I mean negative ions, negative ions, which are fixed here, right? So there will be a Coulombic interaction between these. Okay, so this will also affect the movement of the holes in the valence band. So this is exactly the same way we said. Okay, so this Coulomb interaction produces scattering and affects the mobility, or you can say the velocity of the charge carriers. Okay, which can be actually written as mu I, which I will say the mobility due to impurity scattering. This is proportional to what? T to the power 3 by 2 divided by Ni. What is this Ni? T is the temperature we consider. Ni is nothing but the total ionized impurity concentration. Total ionized impurity concentration, which is given by we can write, just now I said Nd, if you are giving, then you will get Nd plus number of impurities here. Na, if your doping concentration is Na, then you will get Na minus amount of impurities here in this case. So the total impurity that gives you Nd plus plus Na minus. Okay, so this is your Ni value, right? So if the number of ionized impurity center increases, then the probability of a carrier, charge carrier, encountering an ionized impurity center means these are the ionized impurity center, will increase. Okay, will increase, right? Implying what? Smaller value of mobility, smaller value of mu I, smaller value of mu I. So the mobility will be affected. So, right? So more the number of, this Ni value, you can see it is inversely proportional. So more the number of impurity atoms you are adding, more number of ionized, these ions will be, ions, impurity ions will be created, and more strong will be the Coulombic interaction between the charge carriers, which is capable of moving in the conduction band and valence band with these impurity ions. Okay, and the mobility will be affected. Okay, so this is how we can consider, we can think of ionized impurity scattering, and how these ionized impurity scattering is going to affect our mobility, right? So similarly, a graph can be actually plotted between this total impurity concentration, which we said Nd plus plus Na minus, considering that both the dopant atoms, impurity atoms. Okay, so this is your Ni, and if you will consider the mobility over here, okay, mobility concentration is always per centimeter cube. Okay, and here we said this is in centimeter square per volt second, this is the unit. Then it gives you the nature of the graph is something like this. Okay, so initially, for small value of impurity concentration, you can see small value of impurity concentration, it is not that affected. You can see that it is not that affected. This region you can see not affected, but as it increases, the impurity concentration here increases for larger value of impurity concentration, you can see that there is drop in your mobility. Okay, so this is how, this is for room temperature considered to be 300 Kelvin. Okay, so this is the graph for mu n, and for mu p, the whole concentration, if you will see, it is little different with a little steeper than, sorry, one second. So this is little steeper than the mu n graph. So goes like this, and then there will be little more gap like this. Okay, so this is for mu p, the mobility of the holes will be affected, how the mobility of the holes will be affected by this impurity concentration. So for the same impurity concentration, you can see the electron mobility is little higher, you can see the gap here higher than the whole mobility. Okay, so this is the variation of mobility with respect to the impurity concentration that is added in extrinsic semiconductor. Okay, so thank you for watching this video, stay tuned, thank you.